This talk is about the Memory Access API, which is a new API which we added as an incubating API to Java 14 just as the gate was coming crashing down. So basically on the very last day. And the title of this talk is deliberately inflammatory. I hope that by the end of this talk I will have convinced you that the role of the new Memory Access API is not to completely replace the ByteBuffer API. You can decide whether you want to use the new API with ByteBuffers or if you want to completely replace ByteBuffer usage with the new memory API. So it's up to you. Hopefully you will have yet another tool in the toolbox that will help your work. So usual disclaimer, don't believe a word I say. So there are a number of situations as to why people may want to reach for off-heap memory. Probably the primary one is to avoid all the costs associated with GC. Now we have Shenandoah, we have ZGC, so we have much better GC than we did in the past, but still there are cases where, for example, when you want to do a real-time application, you may just want to entirely avoid GC poses. There are also other circumstances where using off-heap memory may be necessary. For example, when you want to share memory across multiple processes, or when you want to share memory with a native library. So it's not an accident that we landed on this API when we were working on Project Panama, which is, as Mark showed before, all about kind of native interop. The Java de facto API for using this kind of off-heap access is the ByteBuffer API. There are also other APIs hidden in the JDK. Misc and Safe is some Misc and Safe is one of those. You can use that if you want. It's fast, but it's unsafe. So if the VM comes crashing down, it's your fault. What about ByteBuffers? Well, ByteBuffers were added in Java 1.4, so they were part of the big push towards buffer-oriented input-output. They are a rich and stateful API, and one of the main drivers of ByteBuffer was to make it simple for you to write idiomatic I/O code. So it has a lot of state internally that allows you to prevent buffer overruns and underruns, helps you with things like charset encoding and decoding. And ByteBuffer, crucially, can be allocated both on the Java heap, but also off the Java heap. So you can actually allocate a slice of off-heap memory and associate it with a ByteBuffer. This is like a very typical example of ByteBuffer usage. Basically, we want to read the contents of a file channel into a ByteBuffer, and then we want to do a loop to read all the characters that we've read from the buffer. So when we allocate the buffer will be empty at the beginning. Two notable things. We have quite a bit of variables here. There is a position, which is initially set to 0, and then there is a capacity, which is essentially how big this buffer is. In this case, it's 10 bytes. And then there is a limit, which is another mutable part of the state of the ByteBuffer, which will be initially set to the capacity. The first thing we have to do is, well, we have to read some stuff from the channel, which means we are actually writing into the ByteBuffer. So here we read some characters, and now we have to start reading them into in our application. So the first thing that we have to do is to flip the buffer from writing mode into reading mode, which means the position here will be set to 0, and the limit will be set to the maximum, basically to the position after the last character that has been read. So I can start doing my loop and read all the characters one by one until eventually we'll end up in a state where the position is identical to the limit. In this case, the predicate as remaining will return false, which means I will go out of my loop, and then I have to get ready for yet another read from the file channel. So I have to call clear. And what does clear do? Well, it will basically reset the state of the ByteBuffer to the initial state. So position will go back to 0, the limit will go back to the capacity value. And so I can do another iteration. And that's basically how you work with buffers. Of course, if you wanted to, this is a buffer that is allocated on heap. If you wanted to use a buffer off heap, you just change a single line of the code here, use the allocate direct instead of using the allocate method. So this is called a direct buffer and is associated with off heap memory. So with direct buffer, we actually have a new weapon as developers, because we can write code that allows us to access off-heap memory. Access to off-heap memory with ByteBuffer is quite efficient, because at the end of the day, ByteBuffer is implemented on top of unsafe, so we can still get advantage of all the C2 data movement intrinsics that we have. The access is also safe, because as we've seen, the ByteBuffer have all this concept of capacity, limit, position, so every access will be within the boundaries of the ByteBuffer, otherwise we will get an exception. But how good are ByteBuffers if we want to write general kind of off-heap programs? Well, let's try to look at some numbers, right? Here I have a benchmark, which is essentially allocating a slab of memory, 400 bytes, and then is setting 100 ints inside this big slab of memory. The benchmark has been kind of cherry-picked, because I think this benchmark is characteristic of what happens a lot when you do native interop, which is something that we care a lot when we do Panama. So you allocate a small buffer of memory, you fill it, and then you have to pass a pointer to this memory to maybe some native function, and then you have to free the memory after the function returns. So this is maybe not a use case that comes up a lot when you're doing I/O, but this is something that you do quite typically when working with native libraries. So if you use unsafe, you get a certain throughput, so 9 operations per microsecond, that's fine. Let's try to replace this code by using the ByteBuffer API, which is a supported API. We can see that the throughput is almost 9x slower compared to unsafe. This is due to the extra safety that the ByteBuffer API provides, but it's also due to a number of extra factors. Here we can see that there are at least 2 factors that are hindering performances. The first is that I'm using the relative positioning scheme, so I do a putInt, and I'm basically relying on that mutable position field that will be incremented on every access. And that slows things down a little bit. But the second and most important thing is that every ByteBuffer has to be registered with a GC cleaner for the off-heap memory to be deallocated after we can prove that the ByteBuffer is no longer referenced by anything in our application. And basically the GC has to do a lot of work here. And this work shows up in the benchmark. In fact, if we change the benchmark a little bit, first to use the absolute putInt method, and secondly, more importantly, to use the unsafe invoke cleaner method, which actually allows us to free the memory explicitly without relying on the GC cleaner, we see that the performance rise a little bit. It's not as fast as unsafe, but it's a little bit better. To be fair here to this benchmark and to ByteBuffer in general, unsafe doesn't zero memory, ByteBuffer do zero memory. I'm not allocating a very big chunk of memory here, so zeroing is not affecting performances too much, but still there is an extra cost here when using ByteBuffer. And let's look at what happens in memory. So with unsafe, of course, the GC is basically not working. All the access are unsafe, are off heap, and that's basically what you would expect. But with the first ByteBuffer example that we wrote, so just the naive ByteBuffer usage, the GC was actually spinning for 5 seconds during this benchmark, which is quite a lot considering that you wanted to use off-heap memory to get rid of the GC in the first place. With the third benchmark, so this new version, things get a little bit more under control and the GC time goes back to 0. But still, the performance is not quite as good as it could be. And the biggest problem here is that ByteBuffer allocate direct. That first invocation is quite heavy because the ByteBuffer has to be registered with a cleaner, even if we are not using the cleaner anyway. And also there is quite a complex state in order to track how much off-heap memory we are using. There is a limit, so there are a couple of atomic instructions in order to check whether we are allocating too much. And so this is quite expensive, and it shows up in this particular allocation-intensive benchmark. So where does this leave the ByteBuffer API? Is this a bad API? No, it's not a bad API. It's just that here I think we are trying to use it in a way that wasn't the way in which ByteBuffer were meant to be used at the beginning. Direct buffer work very well if you allocate, for example, a very big direct buffer and then you keep sharing it. And also because the cost of I/O operation typically dominates every other cost. All the stuff that I showed you before doesn't really matter, right? Unfortunately, though, ByteBuffer failed to scale when considering kind of more general cases because you have no way to deterministically release the memory. So you're basically either rely on the GC or you use some unsafe operation in order, but you still pay a lot upfront in order to allocate the buffer. And then you have the 2 GB limit, which is starting to hurt, especially now that we have support for mapping persistent memory files. So a persistent memory can probably be a little bit bigger than 2 GB, and we have no way to access it using the ByteBuffer API because all the indices that we can specify are essentially ints. And then there are limitations with the expressiveness of this API when it comes to accessing the memory, because we can either choose between sequential access, so essentially one int at a time, or another absolute addressing scheme where I have to pass the offset all the time. There's no support for structured access. So if I have a struct in memory, there's no way for me to say I want to access that particular field. I have to work offset manually in order to get to this or that location into memory. So we think that rather than investing more on the ByteBuffer API, the time has actually come to build a new memory API from the ground up. And of course, this new API will be interoperable with ByteBuffer, so you don't have to throw away all your code. But as I was discussing with Paul last week, we think that ByteBuffer have reached their functional capacity. Some of these limitations, such as the 2 GB limits or the deterministic delocation, are very hard to fix in the current ByteBuffer API. It will require a pretty big redesign of the entire API, which is probably not going to be very compatible. So it's probably better to start from scratch and to design a new API here. This is what happens when ByteBuffer kind of fails to meet the expectations. So Netty is a big client of ByteBuffer. It allocates a lot of ByteBuffer, and starting from version 4, they're all in their own version of ByteBuffer called ByteBuff. No pun intended. And this is based on a different allocation scheme. So they have also a specialized allocator, which reuses memory. So it's an allocation pool. And it's essentially a JE malloc implementation written in Java. And with this, they were able to get a lot more scalability out of their buffer infrastructure. And this is unfortunately something we cannot support in Java today, so people have to reach out for different abstraction. So we'd like that code to come back to the JDK eventually, or at least that's the hope. So enter the memory access API. It's a new API. It's a safe API, so the goal here, and we will see that later even more, is absolutely no VM crashes. So you should never get a VM crash while trying to access a heap memory using this API. It's as safe as ByteBuffer are. There are 3 key abstractions. The first is called memory segment, which is just a region of memory, contiguous bytes somewhere. They can be on heap or off heap. The API is actually neutral as to whether the bytes are stored. And then we have addresses, which are essentially offsets into segments. So you can think of it just as a long that points to some location inside the segment. And then we have memory layouts, which are optional description of the contents of memory. You can decide to use them, or you can just decide to ignore them. But we will see what are the advantages of attaching a memory layout to a segment. If you look in the Java doc of this API, you will find no method called getInt or putInt, nothing of the kind. And we have received some question when the request for review went out. It's not an omission because we forgot about them. It's because there are plenty of ways in order to get to the data of a memory segment. You can, for example, take a memory segment and map it to a ByteBuffer. And then you can use the old good ByteBuffer API to get int and floats and longs and never look back at segments ever again. Or if you are if you want to reach lower level and you want to go down the varendle rabbit hole, you can actually create varendles that are able to dereference memory using memory addresses. And this is actually a good option that I will explore in the final part of this talk. So the main idea here is that we don't need to reinvent the wheel. We don't need to add a lot of accessor for our memory. We can just leverage the good APIs that we already have. This is what a segment looks like. Let's imagine that we have an array of struct point, where a point has 2 int coordinates. It's a very simple thing. So we can imagine this array memory to be flattened, so that all the coordinates are essentially consecutive, so x0, y0 up to x4, y4. This segment will have natural spatial bounds, so we will start from a base address, which will point to x0, and then we will have a limit address, which is the maximum address associated with this segment. Actually, it's the address of the first byte that is outside the segment. So as long as the access occurs within the segment, everything is fine. If I have an address, I can add an offset to it and obtain a new address. So for example, if I add 16 to the base address, I will obtain a new address that instead of pointing to x0 will point to x2. And if I have a segment, I can also slice it. This is similar to the slice operation that ByteBuffer also provides. So I can specify a new start address and a new length, and I will get a subsegment which will be contained into the original segment. So nothing too fancy here. The main thing maybe to notice here is that this API is immutable. So there are none of these bounds that you see here are mutable. Whenever a new address is created, you actually create a new instance with a new offset. So nothing will actually mutate in memory, which will hopefully enable for better C2 optimization in the future. The goal of the big goal of the segment API and the big bet is that we want an API that is able to do deterministic allocation, which means whenever you are sure that your memory is no longer going to be used, you should be able to explicitly free it. And the way this is done is that you essentially have a segment, you use it, and when you're done, you close the segment. Of course, with power comes responsibility. If you forget to close your segment and the segment goes out of scope, you have a memory leak, because now you have some memory of heap, and that is not being cleared. To help with that, memory segments implement the auto-closable interface, so you can use memory segment with the try with resource construct. Hopefully that will reduce the occurrences where these leaks will occur. Other things we could do in order to improve on this is to do something similar to what Netty has done, which is to add a debugging kind of mode where we actually register a cleaner and we keep track of when a segment goes out of scope and the close method has not been called on it. So the way you work with segment, as I said, you don't need to do an awful lot. You can just allocate your segment of the right size. So here, if we want to allocate a segment that is big enough to contain our struct of point array, we have to do a little bit of computation. There are 4 bytes for each int, there are 2 ints for each point, and then there are 5 points in the array. And then I can just derive a byte buffer from the segment and then pretend that the segment doesn't even exist. I will just use the ByteBuffer API to put the int for the x coordinate and the y coordinate into a loop. And then at the end of the try with resources, when I close the brace, a close operation will happen. The memory associated with the segment will actually be released. So did I gain anything by doing this round trip between memory segments and ByteBuffer? Well, actually I gained quite a bit, because I got rid of that expensive allocate direct operation. The ByteBuffer that we are creating now is just a view of the memory of the segment. So it's a much cheaper operation to do. And we also have a deterministic deallocation at the end. So we no longer have to rely on the garbage collector to go in and free the memory. We can actually say when the memory needs to be freed. And so if you write this code, you will get the same performances that you could get with the benchmark that I showed you last, that was using an unsafe method to clean the memory. Actually, this should go even faster, because you are paying a lot less for the first allocation of memory with the memory segment of native. There are problems in this code, though, I'm not gonna lie. For example, we have to compute the size of the memory that we want to allocate manually. And then there are all these offset and constant spread all over the code, and this is very fragile. If I change, for example, the coordinates from int to be longs, for example, probably on 64 machine, this example is no longer going to work. So how can we make this code a little bit more robust? Well, our idea was to introduce an abstraction called memory layouts, and the goal of this abstraction is actually to be able to replace that comment, and I showed in the previous slide, so this thing at the top, with an actual object creation. So you can actually create an object which specifies what is the layout of this array of structs. The advantage of doing that is that once you have an object, you can derive all sorts of important information out of it. So for example, how big is your layout? What are the alignment of some of the components in the layout? And since layout can compose, so you can basically nest layouts inside other layouts, you can use layout paths to ask tricky questions such as what is the offset of the field y inside a point, which will be normally have been an handwritten constant, and now you can actually ask the API for that. And you can imagine that when working with more complex structs, this will actually be useful. So the big bet here is that by having more declarative code, there will be less places for bugs to hide. So this is how we model the point struct using a layout. So of course we have to start from the outside. We create a sequence layout. We call it sequence layout. So you have to specify a size, which is 5 in this case, and then you have to specify what goes inside the sequence. In this case we have a struct, so we just call memory layout of struct, and then we have to specify what are the fields of the struct, and there are 2 ints, 32 bits, I'm assuming the ints here are mapped to 32-bit value, and I can even attach names to the fields, so that then I can actually perform queries on this particular layout. So here I've done a little bit of a simplification. In reality, if you try it out on the Java 14 code, the constructor for the value bits will also take an endianness, because of course you have to specify whether you are big endian or little endian, but it didn't fit in the slide, so that's kind of what it is. So let's say that we have this big layout here, which represents my array, and I want to compute the offset of the y field inside a point. How can I do that? Well, there is an handy method inside a layout object, which is called offset, without too much fantasy maybe. You have to pass a path that enable the method to find the field that you want to get the offset for, starting from the outer layout. So here we are starting from the sequence layout. The first thing I have to do is to choose an element of the sequence. Let's say that we pick the element number 0, because that's the one with the least offset. And then inside the sequence, now I have to choose which of the 2 field structs I want for computing the offset. In this case, I want the y field. And so by doing this, I was able to specify a path from the sequence down to the y field, and now I can ask for the offset. So as you can see, I've been able to obtain the offset without writing any number. I'm just essentially querying the API. And that's exactly what we are doing now in this written example. We got rid of the comment at the beginning of the example that we had before, and we replaced it with an actual memory layout instantiation. So now we have an object that describes the layout of the things that we are going to work on. And then I'm able, in the middle part of the slide, to use the layout to derive constants, such as how big is a point, or what is the offset of the y field inside the struct point. And then I can use all this stuff inside my loop to get rid of all the numeric constants. And most importantly, I can use the layout directly into the allocate call for the memory segment, which means I don't have to write the size by hand. I will just delegate to the layout API to do the right thing. So this is much easier to read. We gain quite a lot in terms of expressiveness. There is still a little bit, there is still something that I don't quite like, which is if we go inside the loop, we see that there are 2 calls to the ByteBuffer putInt method. It's pretty hard looking at this code that one call is meant to set one field of the struct and the other call is meant to set a different field of the struct. It's only the offset computation that kind of gives away that information. So that's yet another place where bugs can hide. So can we do a little bit better? Can we improve a little bit on that? And the idea that we got, maybe a crazy idea, was to introduce a new breed of variables called memory access handles. For those of you who are not able or familiar, not familiar with the variable API, you can think of a variable as a Java lang reflect field on steroids, in the sense that a reflective field gives you access to Java fields. A variable gives you also access to reflective access to Java field, but also to more variables, such as array elements or ByteBuffer elements. So it kind of felt natural to also provide a new variable that was also able to give you access to, for example, off memory by taking as a coordinate a memory address. The big gain that you get with this API is that, number one, you get all the atomic operation that the variable API support. So let's say that the ByteBuffer API is not enough. You're not good enough with just a simple get. You want an atomic get or something like that, or you want memory fencing because you're working with multiple threads. Then you need to reach for the variable API. That's probably the best API to do this kind of stuff with. And the second bonus point is that if you are using memory layouts, you don't have to do anything particularly fancy in order to get this variable. You can just ask the layout API, give me the variable for accessing that field, and you will basically get it. So if we want to see how this variable work, there is a factory inside the memory access API that allows you to construct the variables by hand. Typically, you won't have to do that because, as I said before, you will derive the variables from the layouts. But let's say that you want to kind of go through the process and create the variables bit by bit. So when you create a memory access variable, the first thing that you have to specify is a carrier type. So you have to say to the variable what is the Java type that you want to come out of, for example, of a get operation. So in this case, we want to read the value as int because the value are 4 bytes. So we are going to pass the int.class. To the variable factory. And so we get a variable that, for example, if I give the base address of this segment, it will give me back the value of the x0 coordinate. Can I do more? Yes, of course. If I want, for example, to read y0 rather than x0, I can combine my previous variable with an offset. So I can essentially take the address that comes in, attach an extra offset to it, move it, and then read at the second address. And so I can read y0. If I pass the base address, I can get y0 out. But can I do something more fancy? Like, can I access all the y coordinates in this array? Actually, it turns out I can. I can construct a strided variable. So I can pass in the stride. In this case, the stride is, of course, the size of the point. And so I get back a variable that takes an extra coordinate, not just a memory address, but also a long, where the long is a logical index, which basically says which point I want to get the y from. So if I do, for example, a get with an index of 0, I will get y0. If I specify 1 as an index, I will get y1, and so forth. Now, constructing variables like that may be a little bit painful. So we integrated this variable machinery with the memory layout API. So as you can see in the middle sequence of this slide, we can actually derive all the variables for accessing x and y with 2 simple calls to the layout API. There is a variable method, you specify a carrier type, then you specify a path down to the element that you want to access, and so you can construct in 2 lines a variable for the x element, a variable for the y element, and now inside the loop you can see that I'm using the x variable for setting the x elements and the y variable for accessing the y element. So now the code is more explicit, and if I change anything in the layout up there, everything will just flow. So I won't need to update this code at the bottom ever again, hopefully. So let's switch gears a little bit and talk about safety. As I said at the beginning, this is a safe API. So one of the main goals is to avoid any kind of VM crashes. It is beyond the scope of this API to avoid kind of silly user mistakes such as writing an int, maybe reading the 4-byte value as a float. That's not something we want to protect you against. But for example, there are a couple of conditions that we want to protect you against, such as accessing memory out of bounds, which if the memory is off heap can result in a crash, and also accessing memory after the memory has already been freed. The second problem is in particular a nasty one, especially when you consider multiple threads accessing memory at the same time, because you can have one thread doing access and another thread doing the release. So how the heck do we make this safe? It's actually pretty tricky. You could lock everything, but that basically kills the performances. Instead, what we decided to do was to, by default, enforce a strong confinement model, so that whenever you create a segment, the segment is confined to that particular thread who created it. So only the thread has access to the memory associated with the segment. Any other thread that wants to join in can, but it has to do an explicit operation called acquire. This acquire will create a view that is specific to that second thread, and you can only close the original segment after all the acquired views have gone. So we still have deterministic deallocation even in the presence of multiple threads, but if you are working with multiple threads, you have to be explicit on who is accessing what. So how does this translate in terms of performances? This was the best result we could squeeze out of the ByteBuffer API. We had to cheat a little bit by using unsafe. And these are the numbers that are coming today out of the memory segment API. They are still not as good as the unsafe numbers, but they are a little bit better than the ByteBuffer ones. The main contributor, I think, for this number is the fact that the allocation got a lot less expensive compared to the ByteBuffer allocate direct method. But there are also other things. So all the bounds are final variables, so C2 can hoist them at will, almost. And there is still a little bit of a difference. Also, we have to keep in mind that we are also zeroing memory with the memory segment API, so we can never go quite as fast as unsafe here. But we are also kind of trying to look ahead a little bit, and we don't want just to provide you something that looks a little bit better than ByteBuffer. We want to give you something that is actually more scalable, as I was mentioning at the beginning. So we are working on a different allocator. Jim Lasky is doing a bunch of work on this new allocator called Quota-based allocator. And the numbers so far, I'm kind of teasing you a little bit, are pretty impressive, in the sense that after I did some experiment to plug in this new allocator on the memory segment API, I was able to reach better performances than unsafe, even though I was still zeroing memory. So this allocator is doing a lot of the tricks that the NETI allocator probably does, but there are a couple of tricks that I think are new. So for example, we, instead of committing memory eagerly, we pre-reserve a big bunch of memory, like 4 gigabytes, and then we only commit when the client requests memory. And doing this saves performances quite a bit. But the big save is that we don't need a native call for doing a malloc each time we allocate a new segment or each time we have to free it, because the allocator will be able to recycle these memory segments that are being handed out and released. So this is kind of where the future of this API is kind of heading, and I think if we deliver something like this, maybe, or at least hopefully, some of the alternative API to ByteBuffer will over time disappear. Or maybe people that are going to write new API will decide to stay on the main JDK API. How hard was it to get there? Well, I'm gonna be honest, it was a little bit hard. Andrew did some benchmark of this API and found some issues. There are indeed some issues. We fixed some of the stuff in Java 14 already. So for example, Hotspot was very conservative with respect to memory barriers. Every time there was an unsafe access, it will immediately add barriers after the call. Now C2 is behaving a little bit better, and it's removing barriers when the access is probably off heap. And this also improved the performance of the base ByteBuffer API, so that's actually a good result. Thread confinement checks were not very well treated by C2, most of all because the thread.currentThread was not being perceived as a constant by C2. So we did some work, Vlad did some work in order to to fix that, and now performances are a little bit better, although we have to disable this optimization on the loom branch, because this of course creates all sorts of havoc with fibers. But we are not done. There are a lot of issues around escape analysis. This API, as I said, is immutable. Every time you call base address, you create a new instance. Every time you do add offset on an address, you create a new instance. And sometimes these instances go in the middle and perturb some of the C2 optimization, that C2 is not so able to kind of see through some of the allocations. There is also another problem, and this is probably the main problem with this API. This API accepts long as indices, and this is good because it gives more room for this API to grow, but at the same time, we are running into some bottlenecks with C2, in the sense that C2 is optimized to remove bound checks on loops that work on int. So as soon as you step out of ints, you are into an heap of trouble. And the bound check elimination no longer work, loops are no longer unrolled, you don't get vectorization, any of that. So right now we are doing some heroics in order to try to kind of generate the right set of code, but we think that the right approach longer term will be to fix this big performance gap, and at least let C2 to see whether a segment is bigger than 2 gigabytes or not, and if it is not, then revert to the logic and optimization that we already have. In other words, there's more work here to be had. So I think the memory access API is a great alternative to the ByteBuffer API, or a great complement. It is a fully immutable API, so it should lend over time to better JIT optimization. There is deterministic deallocation that you didn't have with ByteBuffer, and that makes quite a difference in terms of GC load. The addressing scheme is not limited to 2 gigabyte, which also makes a difference if you are using persistent memories or things like that. And there is the availability for doing structural access with the variables, memory layouts. So I think it's a very compelling alternative to ByteBuffer if what you want to do is off-heap. The memory access API is safe. It's as safe as ByteBuffer, so it's a good safe replacement for the unsafe API. There are spatial and temporal checks on every access, and there is a robust ownership model which allows you to remain safe even if you are working on multiple threads and still retain the deterministic deallocation. So where does all it fit in the bigger Panama picture? I'm not going to talk about JNI, but I just wanted to give you a taste of kind of where it all fits together. So as Mark showed earlier, we want to, in Panama, we want to give you tools so that you can start from another file, do some work, and derive a set of Java bindings. And these Java bindings, initially we thought, well, maybe they are interfaces with some annotation, and then there will be a runtime component that reads the annotation and will generate some code on the fly. We actually realized that there's no need for that. We only needed two pieces. One is the memory access API piece, which gives you a bunch of variables for accessing the memory, for example, struct fields at particular offset and things like that. The second bit is a foreign function API bit, which we are going probably to deliver in 15 also as an incubating API, which allows you to map foreign function as method handles. On top of these two bits, you are able to create a very low level set of bindings, and then you can also build on top of those. If you want, you can add plugins to the basic tool that we will provide and generate higher level bindings. But the low level bindings, as Mark showed before, are not so bad. We are generating static wrappers, so they are relatively usable. So as I said at the beginning of this talk, this API is actually available in Java 14. So my recommendation is to kind of try it out and report back performance photos or usability issues or whatever you can find. Next steps, of course, are to round up the performance work. We know that we have to do better here. We want also to finish the work on the allocator, because we think there's a lot of room for improvement there. And we have to polish and finalize the API. Right now it's an incubating API. There are probably methods that need to be polished or named or whatever. And then we have to integrate this API into the overarching Panama story. So you can follow the progress on Panama Dev, but if you are more familiar with core libs, you can also report the issues on core libs. I will be looking for both. So thank you.